What we're going to look at in this video is how to come up with measurements for similar triangles using what we call indirect measurements, meaning we cannot actually go and measure, in this case, like a flagpole. Okay, like it's too tall for us to measure. So before we talk about these methods of using indirect measurement, what I would like for you to do is to work on the warm-up and try to answer that on your own, and then we will go over it after you unpause the video. So go ahead and pause the video and do the warm-up. Okay, so it says you shine a flashlight at a mirror and the light is reflected up the wall to illuminate a bug. Why are these two triangles similar? Meaning, how do we know that these two triangles right here are similar triangles? And if you recall from lesson 7.2, we came up with a few ways to tell if two triangles are similar. And one of the ways that one of the shortcuts that we came up with was angle, angle. And what that said was that if two triangles have two congruent angles, then those triangles are similar. So we see that both these triangles have a right angle. So there's one angle that's congruent. And then you have this flashlight that shines a light down here. So you have this incoming angle right here. And then what we know is that the outgoing angle bouncing off the mirror is congruent to the incoming angle. So that gives us two angles. So since we know that two of the angles in these triangles are similar or congruent, then we know that the two triangles are similar. So why are these two triangles similar? It is because of the angle-angle shortcut. Now, what we're going to look at today is how we can use similar triangles to calculate the height of tall objects that we cannot reach. For instance, in this picture over here, how could we use the idea of similar triangles to calculate the height of this flagpole? This method is called using indirect measurement. And so what we're going to do is we're going to take a look at two of the methods of indirect measurement that we can use to calculate the height of very tall objects. So the first method that we're going to look at is called the mirror method. And if we were in person and able to go outside or around the school and do this, we would actually take mirrors and do this activity. Instead, we're just going to look at a picture of a guy standing by a flagpole and talk about how we would do this. So the first thing that you would do is you would choose a tall object. We've chosen a flagpole here. That would be difficult to measure it directly because we can't take a tape measure or a ruler and start measuring that. So you could use a goalpost for football, a basketball hoop, a flagpole, the height of your classroom. But what you would do is you would take a mirror and you would place that mirror on the ground several feet away from the object that you're measuring. Okay, so you can see in this picture, they've placed this mirror some distance away from this flagpole. Okay, so then what you would do is we would measure the distance, px, right here, this distance right there, and I'm going to do that in a different color so that we can distinguish the two. So we would measure this distance right here from your body, from your feet, to the middle of the mirror. Okay, and we would also measure the distance from the middle of the mirror to the flagpole. And what we would do is we would, come up with those distances. I'm going to tell you that the distances here from your feet to this mirror are going to be 50 inches. I've gone ahead and I did this on my own, so it's 50 inches. And then we're going to measure the distance from P to the observer's eye level, meaning from the feet to the person's eye level. And again, it's important to make sure you notice in this method where we are using a mirror, the mirror method, you're measuring the height from the ground to the person's eyes because the line of sight is starting at the person's eyes. So we're going to say that height is 60 inches. Then we also need to measure the distance from the flagpole to the center of the mirror. And we're going to say that is 45.5 feet. And we want to know how tall the flagpole is. So what we're going to do is we're going to set up a proportion using similar triangles. Now, we know, first of all, let's talk about why are these two triangles similar. Okay, how do we know that? Again, we know these two triangles are similar because the angle between the flagpole and the ground and the person's body in the ground is both 90 degrees. And we know that the incoming angle of the line of sight is equal to the outgoing angle, where they can see the top of the flagpole in that mirror. Okay, so we have an angle condition where we know that these two triangles are similar. So now we can set up a proportion using similar triangles to calculate the length or the height of the flagpole. So we have 60 inches is the height of the person. And then the 50 inches is the distance from mirror of the person. Okay, and that's equal to a proportion of x feet for height of the flagpole and 45.5 feet from the mirror. And I'm writing a little bit more description than you probably need to. So what you'll see here is that the first of all, these inches will cancel out, and we're going to be left with a final answer in a measurement of feet. So what we have is, if we cross multiply here, 45.5 times 60, that would give us 2,730 feet, and that would be equal to 50x. Because 50 times x is 50. And then if we divide both sides by 50, we get x is equal to 54.6 feet. So we find out that that flagpole is equivalent to 54.6 feet tall. Okay? So that is how you can use a mirror method to figure out a distance of a very tall object. Is you just come up with the measurements that you can, the distance from the mirror of both yourself and the object that you're trying to find the height of, and the height from the ground to your eyes. You write a proportion doing that, and then you're good to go. Another way that you could write that proportion is you could write it so that you have you could have it where you have 60 inches over x feet, where you are comparing the heights of the two triangles that are created, the two sides of that triangle, your body and the flagpole. And that's equal to 50 inches over 45.5 feet. And if you look at this, if you cross multiply, you get 60 times 45.5 again, which is going to be your 2,730. And then that's equal to 50x when you divide by, if you divide by 50 here, you get x is equal to 54.6 feet. Okay. Now, another way that you can use, another method of indirect measurement that you can use is by using shadows of objects. So we have an example here. It says we have a person that is 5 feet 3 inches tall that casts a 6-foot shadow, and at the same time of day, a lamp post casts an 18-foot shadow. What is the height of the lamp post? So again, we know that these are going to be these are similar triangles. All right. So what we're going to do is we're going to set up a proportion. So what I'm going to do is I'm going to say we know a 5.25 foot person casts a 6-foot shadow. And since these are similar triangles, we know that an X foot tall lamppost is going to cast an 18-foot tall shadow. If we cross multiply here, we have 18 times 5.25, which is 94.5 feet. Or we'll just put that, we'll leave the units off for right now, but we have 94.5, and that's equal to 6x. 94.5 divided by 6, you get x is equal to 15.75 feet. Now again, like I said up here, you can write these ratios, these proportions in different ways, as long as you are, writing them properly. So what you'll see here is I compared, we have this triangle right here. I compared sides of one triangle to sides of another triangle. The other thing that you could do is you could compare corresponding sides in one triangle to corresponding sides in the other triangle. So if we were to do that, what we would have is we know that the height of the person is corresponding to the height of the lamp. So we could say 5.25 feet over x feet is equal to, and then we also know that the shadow, the person's shadow corresponds to the lamppost shadow, so that would give us 6 feet over 18 feet. And again, some things you need to pay attention to. Notice that the numerator of each of these is the person, and then the lamp as in the denominator. If you're writing it like this, you need to make sure that that the corresponding sides match up. So if you're using one triangle in the numerator in your first ratio, you need to use the same triangle in your second ratio. So again, you have 5.25 times 18, which is 94.5. That's equal to 6x. X is equal to 15.75 feet. Okay. So going through these examples, what you need to make sure you understand is the answer to this critical question. It says, to use similar triangles to solve problems, should the ratios compare the ratio of side lengths within one triangle to the ratio of side lengths within the other triangle, or should the ratios of the corresponding side, or should it compare the ratios of the corresponding sides of the two triangles? Okay, and the answer to this is it doesn't matter. You can do it either way. All right, as long as you are consistent. Okay, and what I mean by that is exactly what I said up here. Notice I had the measurement for the person in the numerator here and here, and then I had the measurement for the lamp and the denominator here and here. Okay, so that's what you need to make sure of. So looking at one last example, we want to find the value of x. These are similar triangles. So we have two triangles. We have this little triangle right here, and we have the big triangle. So what we want to do is we want to figure out the measurement of x. So if we compare the little triangle to the big triangle, we have a side of 5 feet is congruent, or the small triangle has a side ratio of 5 to 12. And then for the big triangle, we have x feet. And then the length of this side would be 12 plus 24, which would be 36. So we have a proportion set up. 36 times 5 is going to be 180. And then 12 times x is just 12x. And then if we divide 180 by 12, we get x is equal to 15 feet. So that is how you can solve for the height of that side CB. There are some other ways that you could set that up. Why don't you try to figure out a few ways that you could rewrite these proportions to get the same answer. You should get 15 feet regardless of how you set it up. Other than that, go ahead and begin working on your homework, and feel free to message me with any questions on your mind or in an email, and make sure you ask any questions that you have when you come into class the next day.